Now we are going to look at completing the square and focusing on the methods required to do it. Before we get into completing the square, we have to be very clear on what it means to have perfect squares and why they might be useful to us for understanding quadratic functions and expressions. To begin with, let's start by squaring some numbers. If I take a positive number, or like just 3, and square it, I end up with 3 times 3 is plus 9. If I take minus 2 and square it, I get minus 2 by minus 2, which is plus 4. If I take 0 and square it, 0 by 0 is 0. In each of these cases, regardless of the type of number I start with, I know these are all whole numbers, but it works with decimals as well, any number that we square ends up being greater than or equal to 0. So a positive number squared gives me something greater than or equal to 0, negative number squared, or 0 squared all give me something greater than or equal to 0. And this is true in general. For any real number squared, I'm going to get something that is greater than or equal to 0. So if I have something like this, x to be squared, I don't need to know what x is. It can be any number, any real number that I like. I know that it is going to be greater than or equal to 0. And I know that regardless of the value of x. So long as x is a real number, that's going to be true. And I also know that it's true, this is going to be greater than or equal to 0, even if it's a complicated looking bracket. So if I have x minus 5 to be squared, any value of x I put in here is just going to be, any real number for x I put in here is just going to be some number squared, and that has to be greater than or equal to 0. So I can see that if I have anything squared, if I can put anything inside of a bracket squared, then I know for a fact that that is going to be greater than or equal to 0. And I can use that to interpret quadratics more usefully. So if I take a quadratic like this, y is equal to x squared minus 10x plus 25, can I see how it is going to change as my values of x change? Well, what I can do is try and factorize this, and what I'm going to find is that it's going to be x minus 5 to be squared. This quadratic is a perfect square in the same way as 9 is a perfect square because it can be written as 3 to be squared, or 4 is a perfect square because it can be written as minus 2 to be squared, or 2 to be squared. So when we factorize this, what pattern do we see as we factorize it? Well, to factorize my quadratic, I end up multiplying the coefficient of the x squared by the constant on the end, so 1 by 25, so I get plus 25. I write out my factor pairs for that, 1 and 25, 5 by 5. Well, that doesn't work, but the negative version of it would, so 5 minus 5 by minus 5 would give me plus 25 when I multiplied it together, and added together would give me the coefficient of my x, my minus 10. So what I'm going to do is break up my minus 10x into two equal parts. I'm going to break it up into minus 5x and minus 5x. So y is equal to x squared minus 5x minus 5x. And anytime we do this, anytime that we're factorizing something that turns out to be a perfect square, this is going to happen. I broke my middle term into two equal parts. And that's going to be important for how we continue with completing the square in a minute. If I continue by factorizing this out, I take out my common factor of the first two terms and then the second two terms. When I do that, something else might jump out to me. The number on the end, the plus 25 here, comes from multiplying minus 5 by minus 5. So I break up my middle term into two equal parts, and the number that I get there I multiply by itself to get the number on the end. This is the pattern for a perfect square. Always we're going to end up with having this number, so breaking it up into two equal parts, and then that number squared, or that number by itself, will give us the number on the end. That's the pattern we get for any perfect square. And that's how we are going to create perfect squares in a minute. But looking very quickly at this function's behavior, this allows us to interpret what the function is going to do because it tells us the lowest point that we could possibly get to. because I know that anything squared has to be greater than or equal to 0. So I know that this function, the y output of this function, is always going to be greater than or equal to 0. And if I graph it, this is what it looks like. My graph cannot go beneath the x-axis. I can't get a negative y value out here. Where do I get my smallest value for y? My y is equal to 0. Well, that would be when this bit, the stuff in brackets, is equal to 0. So when is x minus 5 equal to 0? Well, rearranging, you get it when x is equal to 5. You'd have 5 minus 5 is 0, to be squared is 0. That's the lowest value of y I could possibly get out. If I put in another value of x, say 1, I'd have 1 minus 5 to be squared would be minus 4 to be squared, which would end up being 16. So when x is 1, I would end up, when x is 1, I would end up with y being 16, which is bigger than 0. So when x is 5, I get my lowest value for y. I get it as 0. And then for any other value of x, I necessarily get something bigger than that. I get a positive number for my y. Now, continuing on with this, can we use the pattern that we noticed here, where we break up the middle term, the x term, into two equal parts, and then the number on the end should be that number squared. So here we had 10, we broke it up into minus 5 and minus 5, and minus 5 times itself gave us 25. Well, if I have 8x here, and I broke the 8 up into two equal parts, it would be 4, and if I squared that, I'd get 16. Well, 16 isn't the number there, so I haven't got a perfect square this time, but I can still turn this into something that contains a perfect square, and this is what we actually mean when we say completing the square. So let's look at how we would do this in practice. We're going to create this situation where we break this into two equal parts. So what we do is take our x term, and we are going to break it up into two equal parts. So we're going to break that up into 8 all over 2. Breaking it up into two equal parts would mean that we would end up with x is, or the coefficient of x would be e plus 4, and that squared should be the number on the end. So I want to add that on. I want to have 4 squared as the number on the end here. Where I have an 18, I really want to have 4 squared. But I can't just randomly add numbers into an equation because it would change it. So what I have to do is add and subtract at the same time the thing that I want to end up with, because then effectively I'm just adding 0 on and I don't mess up my equation. So I end up with x squared plus 8x plus 4 squared. Half of this, I'd break this into two equal parts, and squaring that number should give me the number on the end. I have my minus 4 squared, so in aggregate, altogether I'm just adding on 0. And I have my 18 still sitting on the end. It hasn't gone anywhere. So I've added and subtracted this thing that I want to have on the end. Well, now this part of my quadratic is in the form of a perfect square. So I can say that this I know factorizes to x plus 4 to be squared. And then the rest of it can come along for the ride. It's going to be minus 4 times 4 is going to be minus 16 plus 18. And tidying that up, I end up with y is equal to x plus 4 to be squared plus 2. Well, I know that this bit, that bit is going to be greater than or equal to 0 for any value of x I put in there, for any real value of x. When is it going to be equal to 0? It's going to be equal to 0 when x plus 4 is equal to 0. So when x is equal to minus 4, I'm going to get the smallest y value I could possibly get out of this function, because when x is equal to minus 4, the varying part of my function is 0, and I just end up with y is equal to 0 squared plus 2. So I can see that the lowest point, what we call the minimum point on our quadratic, happens when x is minus 4 and I can see that y is going to be 2. So that is how we can use what we're doing, completing the square, to find out lots of interesting information about our quadratics. So let's put this into practice with some other examples. So following on the same pattern as we did before, we want to break this up so that we have part of it as a perfect square. So we want to have half of the number in front of the x, because we want to break this up into two equal parts, and then that number squared, so minus 3 all over 2 to be squared, should be the number on the end. So we want to have, where there's a plus 5 there, we actually want to have minus 3 over 2 to be squared. That would give us the form of a perfect square. Now we can't just add that on, we have to add and subtract it on, so we're not changing our quadratic overall. We're effectively just adding 0. So we can do that, and we have x squared minus 3x plus minus 3 all over 2 to be squared. Now this looks quite messy, and it is, but so long as we understand the logic of what we're doing, we should be fine. What we have done now is create this part as a perfect square. So what we can do is declare that part as a perfect square. And you can see we don't square out these numbers as we're working out. I didn't write down 16 here, and I didn't write down 9 all over 4 here to remind myself that it's x minus 3 over 2 as opposed to plus 3 over 2. I'd lose that information if I squared that out there. And then I can square this one out. 9 all over 4 plus 5. And now I can tidy that up. And when we add up our fractions, our minus 9 all over 4 and our 5, which is 20 all over 4, we find that we get our quadratic would go to its lowest point when x is 3 over 2. 3 over 2 minus 3 over 2 would be 0 squared, and then square that as 0 squared. So we would get the lowest value of this function, the minimum of this function, when x is 3 over 2, and our y value then would be 11 over 4. And we will continue on next with some more advanced examples.